Hello, my name is Alastair, and together with my colleague Ewan Crawford, we'll be talking about lessons learned creating ComputeAorta, a toolkit for implementing heterogeneous programming models. We have both been involved in the project for several years, having seen it deployed to various hardware devices, and we're also both involved in the OpenCL standard. Others in the team track various other standards, so hopefully we'll have some interesting insights on how to implement various heterogeneous standards on a range of hardware devices. Sorry that none of us got to meet in person in Munich, but we'll be participating in the conference chat channels if there are any questions, or our emails will be at the end of this presentation. You and I both work at Codeplay, a programming tools company that solves problems in areas such as AI and computer vision, in a range of markets from HPC through to automotive ADAS. To enable us to solve these problems, we have a suite of products called Aorta. This consists of various libraries and tools that help us create solutions to these problems. Key parts of Aorta include ComputeCpp, an implementation of SYCL, a C++ heterogeneous programming standard, and ComputeAorta, the toolkit that this talk is about that enables us to put heterogeneous programming models onto a range of customer devices. This set of tools is organized as a stack. At the top of the stack, we have the domain-specific tools that our customers use to solve specific problems. Such as for AI, we often use TensorFlow, which we accelerate with Eigen, SYCL-BLAS and SYCL-DNN libraries, or we might use libraries that build directly on top of OpenCL, such as OpenCV for vision. Then in the stack we have ComputeCpp, which is our SYCL 1.2.1 implementation. It can run on top of any OpenCL implementation that meets certain requirements. But for this talk, we'll be talking about ComputeAorta, the toolkit that enables OpenCL 1.2 and Vulkan Compute on a range of hardware devices. To do this, we have our own internal abstraction layer called MUX that we create a specific implementation of for each customer device. ComputeAorta's primary role in this stack is to expose the full performance potential of heterogeneous hardware and to provide standards-compliant interfaces for users of that hardware. This requires a design that scales with minimum effort, including when supporting new heterogeneous programming standards, but more commonly when supporting new customer hardware devices. But in both cases, we can't compromise on performance at any stage. So this talk is about our solutions to these requirements via the intermediate abstraction layer MUX and the toolkit of components that we provide to customer teams. Firstly, I'll provide a high-level overview of the design and some of our philosophy, and then Ewan will go into details on some of the aspects of that. So I've already said that ComputeAorta enables OpenCL and Vulkan Compute on customer hardware. But how do we actually deliver that? Here I've separated a ComputeAorta project into 3 different shells. At the outermost layer we have generic ComputeAorta. This is the team within Codeplay that does customer-independent ComputeAorta work. This includes the implementation of the runtime APIs, so that's the primary work for the OpenCL and Vulkan runtime APIs. We provide software implementations of all the built-in functions for those specifications. Mostly that means the large set of mathematical functions in OpenCL and Vulkan. We also provide device-agnostic optimizations. So these are middle and level optimizations that provide benefits for a set of hardware, not just a single piece of hardware. And we also deliver testing infrastructure to customer teams so as they can do a lot of validation. Then each ComputeAorta project is customized for each customer. Generally this is done by a project team within Codeplay, but sometimes it's also done by a team within the customer themselves. The first task of such a team is to produce an implementation of the MUX API for their target hardware, and then write device-specific code and tests on top of the customer driver and compiler to get the OpenCL or Vulkan implementation working. Then we'll be spending a lot of our effort optimizing this implementation. This builds on top of various pieces of customer technology, so a compiler backend, the hardware driver, and almost certainly a simulator for testing. Any of these components may actually happen to be created by Codeplay for the project, but from the perspective of a ComputeAorta project, they are all external components. You and I both work on the generic ComputeAorta project, and delivering projects this way puts some requirements on how we operate. Firstly, an obvious but key point is that because we deliver source to multiple customers, there can be no customer-specific functionality in the generic code. But of course, every customer project involves a large amount of custom functionality, so we need to provide well-defined and documented interfaces between the generic code that we produce and the custom code that will be produced by the customer team. We expect that customer teams will not modify the generic ComputeAorta source, so as when we deliver frequent updates, they'll be able to take them smoothly. But customer projects do still need to extend the behaviour of the code we're delivering, so we need to provide hooks. This enables things such as custom OpenCL extensions to expose specific pieces of hardware or specific hardware capabilities, or maybe to provide a language extension. We also deliver a large amount of testing, so as customer teams can quickly have confidence in the correctness of their code and move on to focusing on performance. A lot of our tests are actually written against the external APIs that we implement, such as OpenCL and Vulkan. Because these are essentially immutable, a valid OpenCL 1.2 test will always be a valid OpenCL 1.2 test for all implementations and across any refactors. However, we still of course have to test our internal components directly. So for example, the MUX API has its own conformance test suite that we use to validate customer implementations of MUX. The ComputeAorta team does not directly modify Clang and LLVM. Instead, we just provide additional passes that can be inserted. This is because different customers use different versions of Clang and LLVM with their own modifications and their own backend. I've described ComputeAorta as a toolkit, and this slide gives an overview of some of the items in that toolkit. Ewan will describe some of these items in more detail later on, so here I'll just give an overview. At the left, we have the heterogeneous standards that we implement, such as the OpenCL API or the Vulkan API. These are generic components that are delivered in identical form to all customers that require them. These are written on top of the MUX API that will be described later on. And then we have multiple implementations of the MUX API. So we have the reference host CPU implementation that will be covered later. And of course, each customer project has their own custom device implementation of MUX. Then in the center of this diagram, we have some of the items in the toolkit that are shared across some implementations, but not all. So some of the generic components, such as the SPIR-V parser, are shared between the language runtime implementations. So OpenCL and Vulkan APIs both use the same SPIR-V parser, even though they require different dialects of SPIR-V. But most of the items in the toolkit are to be taken and chosen per each MUX implementation. So for example, we provide pre-written implementations of the OpenCL and Vulkan image and math requirements, and a large amount of compiler technology that allows optimizations, such as a whole function vectorizer, DMA optimizations, or custom work item implementations. And finally, on the right of the diagram, we of course deliver testing components for each of these. In particular, one that hasn't been described previously is lit tests for all our compiler technology. I've mentioned MUX a few times already in this talk. That's because it's central to the ComputeAorta design. We implement the higher level APIs on top of MUX, so that's Vulkan and OpenCL, and also more recently we've been investigating level 0 as part of the Akaran project. And then we provide multiple implementations of MUX, either as reference implementations within the ComputeAorta project, or customer teams produce their own implementations. But how does that actually work? Simply, MUX is a written specification. Just like OpenCL or Vulkan have a written document describing how those APIs work, so we do for MUX. And customer teams read the specification and produce their own implementations. It is called MUX because it multiplexes from APIs to multiple hardware device targets. Because customer teams are following its written specification and implementing it, they have complete freedom to implement it however they feel best suits their target hardware to achieve the best performance. As an API, MUX is lower level in OpenCL, but at a similar level to Vulkan. Just like OpenCL and Vulkan, MUX is a C specification. So why did we decide to go that route? Firstly, it provides an easy way to have a well-defined interface between teams as well as between pieces of code. This is important as we need to separate the intellectual property of customers from what we work on. But why not define a C++ interface with abstract classes? Because ComputeAorta is actually written in C++, and so far all customer implementations of MUX have been written in C++, so why have a C API in between them? Firstly, it's easier for humans to reason about a written specification compared to a C++ interface document. And also things such as types in MUX are completely opaque. Customer teams can implement them containing whatever information they require. Or not, if that may happen to be the case. Such a C++ approach would be closer to how software such as POCL works. But compared to that, we feel our approach gives customer teams complete flexibility. Which is not to say that POCL does not provide flexibility. It is of course implemented in a large range of hardware itself. But the MUX approach allows us to very easily make use of custom hardware driver code or intrinsics, to have completely custom workgroup scheduling per each hardware device, and to do more advanced things such as integrate with device debuggers that may use non-standard APIs. An even bigger question is, why didn't we choose to build on top of an existing standard rather than writing a new specification? This is quite a common approach, and indeed even within Codeplay, we implemented the SYCL standard on top of OpenCL. And recently, there has been an open source project that implements a large amount of OpenCL on top of Vulkan called CLVK. Vulkan specifically is quite attractive for building higher level models on top of, because it provides precise control to the developer. And the MUX design was strongly influenced by Vulkan because of this. But at the current stage for Vulkan, we would have had to extend it a large amount to be able to provide full OpenCL conformant functionality. So at the point where we are creating this project, we created a new API, MUX. This enabled us to have full control over exactly what API entry points we wanted. It's important to not have any additional things because this work gets repeated for every customer project, so it must be minimized. So therefore, we want to avoid having to stub out undesired features or to implement things merely for the sake of meeting conformance. And because we have this internal API rather than external standards, we have a large amount of control over how we change it, and we don't need to preserve too much backwards compatibility. Of course, we have to justify all changes to customer teams because we may be asking them to do some small amount of work to match any changes. But it means we can quickly iterate on what needs to change based on what our current customer requirements are. In reality, the only reason to be using a low-level API such as OpenCL or Vulkan is because you want to be able to extract the performance that heterogeneous hardware can deliver. So what philosophy do we follow to enable that? Our key goal is to make it possible for programmers to write code that achieves near to 100% of the absolute performance on customer hardware. If we can achieve this via compiler optimizations, that is great. But that is only a viable approach if it will work in many cases. Often we're working with unusual code that is targeting unusual hardware. And indeed, both OpenCL and Vulkan are low-level APIs where programmers expect to do some amount of work to be able to get to maximum performance. So therefore, in a customer project, we normally also provide extensions for exposing the specialist hardware so as a programmer can directly program them themselves. Customers tend to be interested in performance even in the early stages of a project, as the question of will it be fast enough is actually the highest risk part. It's easy to believe that it will be correct by the end of the project, but knowing whether or not it will be fast enough requires some demonstration. This is where having pre-written optimizations helps, as it allows us to give some demonstration of what will be possible. Finally, we also software emulate features if required, i.e. for not supported by the hardware. And then we describe the consequences of using these features in the optimization guide. In the future, OpenCL's deployment flexibility should provide other paths for this. But even still, it's very useful to run a large amount of software out of the box and then optimize them as required. Now I'll pass over to Ewan, who's going to describe some of these aspects in more details.
Thanks, Alastair. Hello everyone else, I'm Ewan Crawford, and I'm going to be talking to you about some of the implementation details of ComputeAorta, both above and below the MUX abstraction layer. Beginning with on top of it. So a crucial component of supporting a wide range of APIs is enabling their kernel languages. In the case of OpenCL, this is primarily OpenCL-C and SPIR, but also SPIR-V as being the real primary method of supporting a wide range of heterogeneous APIs, including Vulkan and Level 0, and then OpenCL through the CL create program with IL extension as a core feature later on after 1.2, and really for enabling SYCL and other technologies up the stack in ComputeAorta, having a component that translates SPIR-V into LVMIR so we can pass it on to the back end is absolutely critical in achieving our goals. And one of the nice things about ComputeAorta is that we just use a vanilla LVM when we're doing our build. So we've not modified Clang, we've got no merge conflicts or anything like that when we're trying to stay up to date with TIP, and we can get all the latest and greatest features that are available in that project. And any new kernel languages that come about, we can get upstreamed into Clang. We can see them, and we can also push back any bug fixes that we find, and that's always really nice to be able to contribute back to our community. Another aspect of compilation is that we support online compilation, which is jitting essentially in the driver, but we also support offline compilation, where a developer could compile their device-side program with an offline compiler tool just on their desktop, and that'll take the program down to a binary format based on ELF, and we can then load that into ComputeAorta, which in OpenCL would be like CL create program with binary, and that can then run directly. And we support doing a compilerless build runtime, so it has much less C++ dependencies, and it uses a ELF loader with handwritten, so also have reduced dependencies, so that build is much smaller and is more suitable for something like an RTOS, where we can load a pre-compiled binary onto, or some other more embedded device where you don't want to be running a compiler on it at all. You want to be doing that much further in advance. But what if OpenCL-C can't express some of the novel aspects of a customer target? There might be some innovative memory address space that needs to be expressed, or some data type that's really fundamental and you want to have a primitive for it. Well, ComputeAorta exposes some CMake hooks to customer teams that allow them to express this through extensions without compromising the IP in the generic codebase. So we've got runtime extensions, which modify the behavior of the runtime API. So that could be for allocating memory or freeing it or mapping it. And the compiler extensions could be for a primitive data type that you want to express, or for a new address space to represent that memory. That's an example. Our Vulkan implementation is called VK, and it's compute-only implementation. I've used a couple of shortcuts in order to get it up and running quickly. One of those was to use some of the OpenCL math library built-ins in implementation of SPIR-V extended instructions. So there's a couple of extended instruction sets we support. We support OpenCL ones, which using the OpenCL math built-ins for. exactly matches the precision requirements, which is nice. But there's also the GLSL set of instructions, and we're overly precise for those, which means there should be some room here to achieve extra performance by using less precise implementations. However, if this is a concern for customer teams, they can't override them themselves with their own implementation. And that's where math functions like sine, cos, tan, square root. And another shortcut we use is to use some of our OpenCL work item built-ins for the SPIR-V compute built-ins. So things like global invocation ID and local invocation index are implemented using the mangled names for get global ID and get local ID, and that means that any customer teams that have like optimal implementations of these just need to implement them once, and then both Vulkan and OpenCL will work on top of them. So it's nice not having to define these things more than once. One of the interesting things we found is to do with the abstraction granularity of MUX, which is lower level than Vulkan, but much closer to Vulkan than OpenCL is. So having this difference in abstraction layers, although it requires more code to implement OpenCL on top of MUX, actually provides a bit more flexibility when there's a mismatch. Whereas in Vulkan, if we have a mismatch between our MUX API and some of the concepts in Vulkan, dealing with this over a much shorter abstraction space is actually a lot more difficult. An example of something, however, that maps quite well is MUX descriptor types for specifying the data of a given kernel parameter, which is pretty much an exact mapping to Vulkan. So our VK implementation on top of MUX, in a lot of cases, is up as much in terms of lines of code is much smaller than our CL implementation for OpenCL. But sometimes things can map awkwardly. An example of that is synchronization types. So in MUX we've got a semaphore type, which I'll talk about more in the next slide. And a lot of that, and that's quite useful for OpenCL events, but Vulkan synchronization is much more fine-grained. There's several primitives that are being used. And level 0 events for synchronization are even more complicated. They can work across multiple devices and even processes, I believe. Another thing that can be interesting in terms of the modeling several APIs on top of one is that in the case of subtly different behaviors, we find that we can't take we're more conservative and take the more constrained model. So an example is OpenCL queues execute in order by default, although they can execute out of order if you pass a flag. But Vulkan queues execute commands in arbitrary order. So we take the more constrained model here in MUX and we go for OpenCL execute in order by default, or as if in order, as the exact specification wording. Going into more depth on this mapping between Vulkan synchronization and MUX synchronization primitives. So there's 3 synchronization primitives Vulkan, well, I'm going to talk about at least. There's VK fence for one-way coordination from device to host. There's VK semaphore for device-only synchronization within a command queue. And there's VK event for bidirectional synchronization between device and host, which is powerful but more expensive. Whereas in MUX, we've got a kind of single synchronization primitive that does one-way coordination from device to host and device-side synchronization, which is really good for mapping to OpenCL events, but it's not quite so great for mapping to Vulkan. And ideally what we'd have is we'd rename MUX semaphore to like MUX event and then create a bespoke MUX semaphore type for having efficient device-side synchronization. Fortunately, one of the nice parts about MUX being an internal standard is just something that's absolutely on our to-do list, and we can change this and we don't need to be especially backwards compatible. There's also a slight difference of behavior in terms of signaling. So when a MUX semaphore is signaled after a wait operation, it isn't reset. I believe this is the case in Vulkan, so that's a bit of extra work in our Vulkan code to support the case where our Vulkan application submits some work that waits in the semaphore and then signals the same semaphore again when it's completed, because it'll have been reset after the wait. And that's something that, yeah, it would be valid Vulkan code that is a bit more extra work to do supporting MUX. Now that I've talked a bit about building open standards on top of the MUX API, I'm going to go on and talk about how we implement the MUX API for customer targets. Our generic ComputeAorta codebase provides a reference CPU implementation of MUX, which the generic ComputeAorta team develops, and this is called host. And on it, the device-side kernel code runs into the same process as the host runtime code in the CPU, just via a function pointer. This CPU could be a desktop CPU at most developer machines, but it could also be a small embedded CPU on a heterogeneous device for housekeeping. And towards that end, we test the host or host reference cross-compiled, 32-bit ARM, 64-bit, and also there could be for other targets like MIPS. And we run these natively for testing. We also run them under emulated environments like QEMU. So we provides a really nice testing base for developing our toolkit components. And it's also handy for tracking performance changes over time. As a baseline, we can see how the effect of changes to the code base influences host, and that will give us a rough representation of how the impact of these changes also in device targets. It's also really nice to debug something that's running in the same process. That's a lot easier than trying to remotely debug something that could be on a device that's in a separate process using much more complicated debugging tools. One of the challenges we've encountered when trying to get performance on some of our customer targets is how to effectively dispatch work to them. So on low power targets, building up a command stream can be quite a big expenditure of resources, and it's something you don't want to have to repetitively do. If you have repeated commands, you just want to define that once and then redispatch it. And many APIs provide a way of doing this. Vulkan has command buffers, Level 0 has command lists, but OpenCL doesn't actually have a mechanism for achieving this. You just constantly enqueue commands to the command queue, but there's no way of building up, a group of commands and then dispatching that group and then dispatching that group again, for example, for that repeated clustering. And this is something that MUX exposes. Is mapped very similar to Vulkan command buffers. So what we've done to solve this is to kind of map our OpenCL command groups down to MUX and make them as big as possible. So we keep on adding to those MUX command groups, trying to make that cluster of work bigger and bigger and bigger until there's some sort of blocking event or flush, at which point it'll be dispatched. So one of the nice parts about this is that we the generic ComputeAorta team define it for our CL implementation, and then that big command group that can get sent to all of our customer implementations of devices. So we do this once, and all our customers benefit from it. So we create something called a pending dispatch, where we track all the information associated with that OpenCL enqueue call. Things like the command group, any MUX semaphores that are being waited to fall on need to be signalled, and the OpenCL events that are waiting on need to be signalled, and the callbacks. So we track all this state in something called a pending dispatch, which is a command group that's due to be executed but isn't currently executing. The analysis our CL code on top of MUX does when it gets a enqueue call with a wait list is kind of split up into a few cases. So when there's no wait events passed by the user, then we can just push that command onto either the current command group that's not been dispatched yet or the last pending dispatch. If there's wait events, but they're all associated with a single pending dispatch, we can just push that command onto the command group associated with that pending dispatch. However, if the analysis gets a bit more complicated and there's wait events associated with several pending dispatches, or that pending dispatches have already been dispatched, then we just get an unused command group, and that's either newly allocated or it's one that's already been used but has been since reset and is cached and available to push something new onto it. But really what the important point of this is that we're doing this analysis in the generic CL code so that all our devices can benefit from this batching of commands, and they can all take that large command group and dispatch it on the queue as efficiently as it is as possible for their hardware for OpenCL, which wouldn't expose this in the standard. Now I'm going to go on to discuss a few of the Toolkit modules that are available to help MUX implementers. We have our Abacus Maths library, which is a C++ implementation of all the OpenCL Maths built-in functions, as well as some from other languages, to those precision requirements for all of half, float, and double widths across all the vector variants. And it doesn't use any of the C++ standard library, and that's because it gets compiled by Clang down to bitcode. And this bitcode is then actually embedded in the library. So in Linux that would be the libopencl, and its .data section of the ELF will be where the bitcode gets embedded. At runtime, when we compile our kernel and we find these maths definitions, we load the .data section bitcode and we just link in the ones we need. And that's how we integrate it. We could remove this size constraint from our shared library by doing an offline compile of our kernel down to binary, and then we wouldn't need any bitcode at all in the ELF binary. However, by doing it this way, it also allows our MUX implementers to override any of the software definitions and Abacus that they need. So they might not need a software implementation of the square root, they might have hardware functionality for that, for example, or want to use intrinsics or other more performant methods, and they are absolutely at liberty to override the Abacus ones. Another toolkit component ComputeAorta provides is our VECZ compiler optimization, which vectorizes horizontally across a workgroup, primarily in OpenCL, and splits up into SPMD packets of work items, which get executed in parallel. And the reason this is in our toolkit rather than always happening in the CL runtime is because it might not be appropriate for all architectures. If this was targeting some hardware without any vector instructions, then this would be eager optimization, whereas for a target that has really wide vector lanes, this might be absolutely crucial in getting that performance. So for that reason, we provide it as a toolkit component that's highly configurable, but we don't mandate it as part of our runtime. One of the nice things about vectorizing horizontally across a workgroup is that it doesn't depend on identifying special patterns like loops inside a kernel, which all kernels might not contain, and this is what is relied upon for vertical vectorization, for example the LLVM loop vectorizer. And although VECZ is a generic component that we provide in ComputeAorta, it's highly configurable by customer teams because they're going to have their specific architecture vector instructions, vector width that's optimal, instruction pipelines, we need to cater for them. Otherwise we might be actually harming performance by overly optimizing by doing vectorization. So in that regard we can provide like a heuristic cost model that customer teams can fill in to guide the vectorization. We can tweak the optimizations inside VECZ, things like branch on superwords condition code, partial linearization, different kind of predication and masking. And we can also just set the vector width for the SPMD packets, which is really important. If you'd like more information about VECZ, we actually did a LVM dev meeting talk on it back in 2015. I'd really recommend checking it out because it's a very cool optimization. Testing is something we put a huge amount of effort on in the project. It's a real focus of our work, but it's not particularly revolutionary. We have a lot of unit testing for the various APIs we implement that gets in every merge request, and we've got a lot of CTS testing, but also some lit testing for compiler passes, and fuzzing, which is quite cool. So we've got both compiler fuzzing and runtime fuzzing. UnitCL is our unit test suite for OpenCL, and that's got a couple of niceties to it, in that when you have a test category called execution tests, and we define a kernel and OpenCL to run and expected outputs. But we only need to define the kernel once, and we'll test it for both our OpenCL C compiler, our SPIR compiler, our SPIR-V compiler, and our offline compiler, and make sure they all have the same result, and they all have the same behavior. So that's really cool, and it also ties into our OpenCL extension mechanism. So customer teams that have used the extension mechanism can also define their own UnitCL platform specific tests for their own behavior, and they can integrate them into the UnitCL binary and run them all together as a single regression test suite. And the nice thing about implementing Kronos standards is that they stay immutable across anything we should change internally within the code base. So they provide really good regression test suites, because once you've said this is conforming to the spec defined behavior, it's a valid test, then if anything changes internally that would invalidate that, you can catch it. So one of the benefits of having such extensive unit testing is it means we can avoid finding bugs in some of the larger software we support. So when running ComputeAorta underneath something like ComputeCpp, or as part of a more complex machine learning library, some of which are listed here, if you have a bug or some sort of issue, it's a lot harder to track it down through that code stack. So thanks to our unit testing, we can find a lot of these issues much earlier. And this is a range here of some of the software we support, and we're constantly adding to this. Every time customers might come to us and say, yeah, we want to support this benchmarking library, want to achieve this level of performance, we want to support this framework, we can add it to our ecosystem testing and can make sure that ComputeAorta is meeting all the expectations for that. And that's all from my portion of the presentation. So I'll pass you back over to Alastair. He'll talk about some takeaways from our time designing ComputeAorta.
Thanks, Ewan. Through this talk, we've shown that supporting multiple heterogeneous standards on a variety of devices requires making use of reusable components where possible, so as to minimize the amount of work per project. However, if custom components are required to achieve performance, then that must be allowed as well. Over the years of supporting multiple customer projects, we've learned that it's hard to predict in advance which parts will need to be customized, as exposing heterogeneous hardware capabilities is quite complicated. Each new customer device has its own unique capabilities, so it's best to follow an overall design approach that allows for flexibility, so as when the next customer project comes along, we can adapt as required. The way we do this in the ComputeAorta project is primarily through the MUX API. This allows us to minimize the effort to implement a heterogeneous API on a new device, to enable high-performance programs on customer hardware, and to scale to supporting new standards as required for incoming customer requirements. Thank you for taking the time to listen to our talk. We'll both be on the conference chat channels if you'd like to ask us any questions, or if you prefer, you can send us an email.